Questions about the exam extra credit that you'd like me to go over today? Remember, it's due next Monday night at midnight, 11:59 p.m. You can ask for help. Myself or my TAs will help you. We're not going to confirm or deny the answer, but we can help you get better off, better understanding of where you're at. Other thing I want to say is just I think the test was about the right length in as far as time. People were getting done kind of where I wanted to. I think it was probably where I wanted it in the area of complexity. I know that some of you, I've gotten a bunch of emails saying I think I bombed the exam, and I've looked at it and I thought you didn't bomb the exam. You may have not gotten problems exactly right, but there's a lot of partial credit there. And so we'll see. I'll ask you to refrain from really judging where you are until you actually see your grade. I think that I'm more concerned about your process, and even if you messed up what you might consider a major part, if you showed me a lot of thermodynamics work, you're going to get a lot of points for that. So we'll see how that comes. The other thing I will say is that exam 1 is not indicative of how you're going to do in this class. If I were to give you an exam that's going to be indicative of how you're going to do in this class, it's exam 2. Exam 2 is the one where really things take off. I've seen people do very poorly on exam 1 who've done well on exam 2 and just have been successful. I've seen people that have gotten very high scores on exam 1 and just kind of relaxed and said, oh, thermal was not as bad as what I thought it was, and then have really fallen off. So my concern with you is how well you know this next material. That's going to be really the thing that's going to be important to you. And so today, what we're going to do is go over one problem in depth and talk about a corresponding problem to that it is going to be similar. And I probably won't get enough time if the 8:30 class indicates to go through it completely, but I want to make sure that we can go through the process, because what you're going to see right now, this is what a thermodynamic problem is going to look like for the rest of the semester. And it can be frustrating. And it can be, it doesn't show you exactly where you want to go, but we're trying to learn how to think through the process. And so here, again, I'm going to get on my soapbox and say, if you are using an outside resource to do your homework, it's going to start right now to really, really, really bite you, because we have to think through these problems. We have to figure out what it's trying to tell us. And that is something that when it's shown to you, when I'm showing to you in class, it's going to say, that's easy, that's straightforward. But it is making those connections that's what we really have to work on. That's what we have to work on in our homework. Okay, so if there aren't any questions, I'm going to go ahead here and start on this problem. And if you have questions during the lecture, please raise them so we can talk about it. But we're going to refer to this picture, and we have water containing a piston cylinder assembly initially at 1.5 bar and a quality of 20%. So immediately when I see that information, I'm going to start saying state 1. It is a pressure of 1.5 bar, and the quality is equal to 0.2. It is heated at a constant pressure until the piston hits the stops. Heating then continues until the water is a saturated vapor. Show the process of the water in series on a sketch of the TV diagram. Okay, I've asked problems like this before on exams, and my goal here in these sessions is to try to bring problems that people usually have a little trouble with, and this is one of those they have trouble with, because they don't realize that instead of having 2 states, this problem has 3 states that we need to deal with. So let's talk about that. We're going to have state 2, and then we're going to have state 3. We know that there are 3 states because there are 2 different types of processes that are happening here. Remember, processes go between 2 states. So the first process between these 2 is going to be a constant pressure process until this piston hits those stops. And once it hits those stops, Now, as we add more heat to that process, we are going to have a constant volume process, but the pressure is going to change. Okay, and we need to denote these things very clearly. Now, it says here that we're going to continue the heating until the water is a saturated vapor. So that means our final state is a saturated vapor. Okay, they give us that information, and then they say, find for the overall process, evaluate the work. So they want to know the sum of all the work, which is going to equal the work from 1 to 2 plus the work from 2 to 3. And they want to find out what is the heat transfer, which is the heat transfer from 1 to 2 plus the heat transfer from 2 to 3. That's what they want to find. And we look at this and we think, well, the first thing we're going to have to really do here is set states. And there are 3 states there. And I know that I had to have 2 pieces of information to solve, to find every state. And right now I don't know if I have it all. Now, we actually do. But it may be not clear to us in the problem. The problem statement just doesn't say state 1 is this, state 2 is this, state 3 is this. We're going to have to decipher what the information is with our secret decoder ring, what's going on here. Okay, what's going on here? So the first thing I want to do is I want to draw a TV diagram because that really will help me. And so I'm going to draw a TV diagram over here. It's asked for in the problem statement. I'm going to draw my vapor dome. And I know one thing. I know state 1 is 1.5 bars and 0.2, so I'm going to draw a line here. I'm going to draw a line here that is going to be my 1.5 bars. Okay, and I know that my quality is 0.2%. Sorry, 0.2 or 20%. So here it is. This is going to be my state 1. Okay, now I have to reason through this problem. State 1 is right there. I don't exactly know where state 2 is. But state 3, they told me it's a saturated vapor. And I know when that piston goes and reaches the top of those stops, and if I keep adding heat, I know that the pressure is going to rise inside of that piston cylinder. I know that from experience, just personal experience, but I also know that from what we've been talking about thermodynamics. Whenever we have a volume that's rigid and we add some heat to it, the pressure is going to keep rising and rising and rising. So we know that we're not going to be at this 1.5 bar line. We're going to be at another line. So let me just draw some other line up here. This is going to be my second pressure. And I don't really care what it is. This is going to be, I'm going to call this pressure 3. And our point is going to be right here at the saturated vapor. This is my point 3. Okay, I've reasoned through it. I don't know enough information about it yet, but I know it's probably someplace there. Where is my state 2? Yes. Okay. We know it's on 1.5 bar because it said here a constant pressure until it hits the stop. So we can go here and put here that pressure 2 is equal to 1.5 bar. Absolutely. And then you said it's right below state 3. Why did you say, you're correct, why does it say it's right below state 3? Because it's constant volume. So the volume doesn't change between state 2 and state 3, and the mass doesn't change between state 2 and state 3. So volume over mass is specific volume. The specific volume is the same for state 2 and state 3, and so we know that state 2 is right here. And we know our process looks like this. That helps us out considerably. Okay, now we still don't have enough information here. I still only know 2 things to set the state 2 and state 3. So I'm still a little stuck. I can't solve my problem yet, but let's go and see how we can work with this. So the first thing I'm going to do is I'm going to find out what my specific volume is at 1, and I think I'm going to need my internal energy at 1, so I'm going to find both of these things at 1 first, because I'm going to be using my first law. And my first law, I often use internal energy, and I often use specific volume. Okay, and how I'm going to do that is by using the quality equation, right? I'm going to use that the value I'm looking for is equal to the value at the saturated liquid plus x times the value at G minus the value at F. And I'm using a box because I can put V or U into this equation and find out where it is. So for those of us at home, I'm going to go to my document camera, and I'm going to go to 1.5 bars. And here's my 1.5 bar entry for water, and I know it saturates at 111.4 degrees Celsius. And I know my specific volume goes from 1.0528 times 10 to the negative third. Remember that. It goes to 1.159, and my internal energy is going to go from 466.94 to 2,519.7. So I'm going to show this right now. I'm going to take that screen off so I can go back to for those of you at home, I can go back and see my computer screen. But let's go and do that. So we're going to say that our specific volume at 1 is going to be equal to 1.0528 times 10 to the minus 3 plus a quality of 0.2 times 1.159 minus 1.0528 times 10 to the minus 3. And I'm going to save us some calculation time by me fumbling around with my calculator and just tell you that the specific volume of 1 is equal to 0.2326 times 10 to the, not 10, no, just 0.2326 meters cubed per kilogram. And then I'm going to go find my, my specific volume, my internal energy. And my internal energy at 1 is going to be equal to 466.94 plus a quality of 0.2 times 2519.7 minus 466.94. And my internal energy at 1 is equal to 877.49 kilojoules per kilogram. Okay, these are some intermediate answers that I'm going to need. And I've completely set state 1 for everything I'm looking for. That's great and all, but I still haven't, as of yet, determined how I can find anything about state 2 or state 3. So I think for a minute, and I say, okay, what do I know about this situation? Well, I know that this is a closed system. What connects state 1 and state 2 together? Well, they have the same pressure, but there's one other thing, and that is they have the same mass. Okay, so let's look at how we're going to calculate mass. I know that mass at state 1 is going to be equal to the volume at state 1 over the specific volume at state 1. That's the mass. Okay? Now, I know the mass at state 2 is going to be equal to the volume at state 2 over the specific volume at state 2. And because my mass at state 1 has to equal the mass at state 2, I know then that means that the volume of 1 over the specific volume of 1 is equal to the volume of 2 over the specific volume of 2. And so I'm going to write this a little differently. I'm going to write this as volume 1 over volume 2 is equal to specific volume 1 over specific volume 2. This is true between state 1 and state 2. Okay, you're saying that's great, Dr. Wanklin. That's great. We still only know specific volume 1. There's still an equation with 3 unknowns. Okay. Let's see, how would we calculate the volume? Well, they gave us some information in this problem. So you kind of have a clue in this problem when they gave us the height here. They gave us that this is 0.05 meters. And so if we wanted to find the area of 1, it would be the area of the piston. Sorry, if we wanted to find the volume at 1, we'd find the area of the piston times that height, and we would get a volume. Now, we don't know the area of the piston. We don't know it. But look what happens here when we do this. if I want to say what volume 1 is, I would say it's going to be the area of the piston times the height, which is 0.05 meters. Now, volume 2 is going to be the same area of the piston, but now instead of being 0.05 meters, if you look up here, the piston is going to go all the way to the top. Now we're going to have 0.05 plus 0.03. We're going to have 0.08 meters. So it's 0.08 meters. That's going to equal my specific volume at 1, which is equal to 0.2326 all over my specific volume of 2. And what you see is that the area of the piston falls out. Okay? So at times, if you don't know how to solve the problem or you have information that you don't know, put it in terms of variables and see if that variable doesn't cancel out somewhere along the way. It may not. It may be that you're not seeing something important in the problem statement, but sometimes something like this shows up. And now, through this, the volume 2 that we find is going to be 0.37216 meters cubed per kilogram. And that's the key to the problem, really. Right here, this information right here is the key. Because now that I've set volume 2, now I know enough information to set the state 2, and I know enough information to set the state 3 because I have 2 pieces of information for both of them because the specific volume of 2 is equal to the specific volume of 3. This is also equal to the specific volume at 3 because of that rigid tank. Does everybody follow me so far? Okay, now that I know that, now I'm going to start trying to answer the questions that they gave me. I have enough information to set the states. I could go up and set the states. And you might go up and set the states in this case, and that will be fine. I'm going to do a little bit quicker of analysis and start to work with the to answer the questions. So they want to know what is the work from 1 to 2, and I have to know what is the work from 2 to 3, and that's going to be equal to my net work, which is what I want. Okay, now one other thing that I should notice here is that this problem asks me for, well, let's just do this. Let me do this and I'll do this separately. Okay. I know one of these works automatically. Work 1, 2 plus work 2, 3. I know one of these works automatically without doing a calculation. Which one is it? 2, 3, and it is 0 because there's no boundary work happening there. So this one goes to 0, we're done with that. I know that work 1, 2, they told me is equal, it's constant pressure work, and I know work is equal to the integral of PdV. Constant pressure work means I can take pressure out of the equation, and I'm going to have V2 minus V1. Now, I still can't calculate volumes. I don't have that area. I can't do it that way, but I do have specific volumes. And so I say pressure times mass times specific volume at 2 minus specific volume at 1. And here, I know the pressure, I know the volume, specific volumes, but I don't know the mass. And so I might freak myself out a little bit if that I don't know the mass. But I want to go back, just like I did here in class on Monday, I need to go back when I'm into a situation where I can't figure something out and go back and read the problem statement. And the problem statement says this: for the overall process of water, evaluate the work and heat transfer each in kilojoules per kilogram. Okay, it's asking me for specific work, kilojoules per kilogram. We're going to divide the mass out of it. So we do have everything we need. If I divide the mass out of it and I get work 1, 2 divided by my mass, this is going to be units of kilojoules per kilogram. It is going to equal pressure times specific volume 2 minus specific volume 1. I'm good to go. Okay, pressure. The pressure was 1.5 bars, right? 1.5 bars. My specific volume 2 is 0.37216 minus 0.2326. This is going to be meters cubed per kilogram. I have some units that I have to work on here. I know that 1 bar is equal to 100 kilopascals, and I know that 1 kilopascal is equal to 1 kilonewton per meter squared. And so bars cancel, a few of my meters cancel, and kilopascals go here, and I get kilonewton meters. This here is going to be a kilojoule, and I get kilojoules per kilogram, which is my correct units, and so now I can go ahead and do my calculation. I do my calculation, and I find that my answer is 20.93 kilojoules per kilogram. I think to myself, does that make sense? And I really don't know about this, the magnitude too much, but I can ask about the sign, because this means that this positive sign means that I am going to be expanding. And that's exactly what I'm doing. So I'm glad I got a positive sign. At least I can say, okay, I'm comfortable with that. And so this is going to be my work 1, 2, and it happens to be my net work. My net work, because I'm adding 0 to that, is equal to 20.93 kilojoules per kilogram. Okay, there's my answer. We've done that many times. Okay? The addition to this thing is here is we have all these properties that we have to find in addition to doing the first law part. Okay? Just like on the exam you had 25 points of finding properties. On the next exam, all the finding properties is in all of the 4 of the problems. So you're going to have to know how to do both the problems and finding the properties all together. Okay, the next thing we want to find is that we want to find out what the net heat transfer is. And so I'm going to write down my first law equations for both things. I'm going to say the change in internal energy from 1 to 2 is equal to the heat transfer from 1 to 2 plus, that's wrong, minus the work from 1 to 2. And the internal energy change from 2 to 3 is equal to Q23 minus W23. These are my 2 equations for my 2 processes. They told me kinetic and potential energy effects are negligible. Okay, I'm going to show you a common mistake that I get on exams like this. They'll go down here, they'll put a plus sign, they'll say, well, this is going to be equal to summation of my heat transfer. This is going to be my net. This is going to be the summation of my work, and this is going to equal 0. And so I know that my Q, my net heat, is going to be equal to the net work, which is 20.93. They'll write 20.93, put a box around it, and turn it in. What is wrong about that analysis? It isn't a cycle. It isn't a cycle. You can only do this when it's a cycle. Okay, so no, it is not a cycle. We can't do this. Now it still has Qnet and Wnet, but what we're going to have over here is the change in internal energy from 1 to 2 plus the change in internal energy from 2 to 3. Now let's look at what these change in internal energies are. These are going to equal to mass times U2 minus U1, and this is going to be mass times U3 minus U2. So at this point in time in this question, you have a breaking off point that you can use to solve this problem. We know that we're going to divide everything through by mass, so this is going to be by mass, and by mass, and by mass, and by mass. And we know that we know U1, and we know these 2 things over here. We would just have to go and set this state, set these 2 states, U2 and U3, and we can solve our first law equation and be done with it. Okay, that is one way to solve the problem. It takes a little bit longer because you have to set 2 states. I believe I can solve this by only setting 1 state, 1 additional state. And so let me show you how to do that way. Again, the way that finding U2 and U3 and solving it is perfectly acceptable. Fine, I don't have a problem with it. But let's see how we can do it without setting that second state. Okay? Look down here what this is going to be. This would be equal to mass times U2 minus U1 plus mass times U3 minus U2. Look, you're going to have mass times U2 minus mass times U2. So this U2 drops out. And this is equal to mass times U3 minus U1 is going to equal to the net heat transfer minus the net work. And now in this equation, we know the net work, I guess I should say per unit mass. And we know U1, all we need to do is find U3 and we're set. And that should make some sense to us. As all the heat is adding, the property of internal energy is changing from 1 to 2. We don't care what path it takes, how it goes. We just care that the heat that is added to it directly changes the internal energy. So we don't need to break it into pieces. We can just look at it holistically. Now the work, we have to break it into pieces because it's a different type of work in the first process and the second process. Okay, so let's go and find what state 3 is. State 3, we say it's a saturated vapor, and we know, so what do we know about state 3? State 3 is a saturated vapor, and we know that the specific volume is equal to 0.37216 meters cubed per kilogram. Okay, so we go to our tables. And we're going to look at our saturated vapor column, and we're going to try to see if we can find 0.37216. And if I go down here, I have 0.3749 or 0.3757. So darn close to this table entry, but not there. Okay, so we're going to have to interpolate. Now, one other thing I can think of is I say, well, maybe I don't have to interpolate if I'm looking in the nice even pressure table. Let's look at the nice even temperature table and see if that will give me the same thing. So the nice even temperature table, I'm going to look and see if I can find 0.3726. Actually, we're farther away here. The pressure table was better, but we could interpolate between these two numbers and get the same value, same answer. Okay, this is just a different way of looking at things. Now, so I'm going to stick with this. I'm going to stick with interpolating here, 0.3726. But let's just say that you're now on this problem and it's the test, and the test is done in 5 minutes and you don't have the time to interpolate and you need to do something, okay? If I were you in this case, I would write a note and I'd say, Dr. Wanklyn, time's running out. I know that 0.37216 is pretty darn close to 0.3729. And so instead of interpolating, I'm going to go ahead and say that that's close enough, and I'm going to use this value for saturated vapor as my internal energy for state 3. Put that down, you answer the question. Will you get it? Would you get it right? No. But I'd take 1 point off and give you 24 out of 25. If you stop the problem here right now and tried to work on interpolating and everything like that and may not get a final answer, you might lose 4 points. Okay, I want you to see what you're thinking about, see where you're at here. Now that should only be done if you're in dire straits at the end of the exam and time's running out. If not, we're going to interpolate. So let's do the interpolation. The interpolation here is going to be one of the ways to do it. 0.3749 minus 0.3157. I need to get over here to my laptop for those of you at home. 0.3749 minus 0.3157 is going to correspond to 2561.2 minus 2567.4. And that's going to be equal to 0.3749 minus 0.37216 all over 2561.2 minus the specific volume, the internal energy at 3 that we're looking for. And if we do that, internal energy ends up being 2561.49 kilojoules per kilogram. It just changed that value. So if we would assume this value, look, we're pretty darn close to it. But this is the exact value. So that's why that assumption works out. And even if you were further away, it would still show me you knew what you were talking about. I'm concerned about what you know. Okay, I'm concerned about what you know. All right, so now we can go here, and now we know this information, and we can solve this problem. We can say 2561.49 minus 877.49 kilojoules per kilogram is going to equal to our net heat transfer minus the value for our work divided by mass is going to be 20.934 kilojoules per kilogram. And we're going to end up, this is actually Q net for mass, that our Q net for mass is going to give me 1,704.93 kilojoules per kilogram. Again, that's a positive value. That makes sense because the problem statement says heat is added to the piston. That matches what I think it should. Are there any questions about this problem? Lots of things going on here. Lots of thinking that has to be done. Okay, we're going to look at another problem that's very similar to it, and I'm not going to have time to go through it in detail here. So what I'm going to do is I'm going to kind of set it up, give you some values, and then it'll be a good study problem, good problem to put a big star on to study for the exam with as we get going here. Okay, so the next problem is this. It says a piston cylinder assembly contains 2 pounds of water. Okay, now they gave me the mass of the water, and now we're in English units, and we tell us initially at state 1, so state 1 is pressure at 1 is equal to 100 psi, and the temperature at 1 is equal to 400 degrees Fahrenheit. The water undergoes 2 processes in series, a constant pressure process followed by a constant volume process. Okay, so once again, we're going to have a constant pressure process, and then we're going to go to state 2, and then we're going to have a constant volume process to state 3. At the end of the constant volume process, the temperature is 300 degrees Fahrenheit, and the quality is 60%. 0.6. Neglecting potential energy effects, sketch TV and PV diagram showing key states and processes, and give me the work and heat transfer for each process in BTUs. So in many cases, this is the same situation that we had before. 2 processes, constant pressure, constant volume. But there's been some changes here. We've given you mass. Now we're starting someplace different, and we're going to a saturated liquid, saturated mixture, when the other time we flipped that around. Last time they asked for a TV diagram. This time we're asking for a TV and PV diagram. So let's see if we can't draw those diagrams right away. So the first one I'm going to draw is I'm going to draw my TV diagram, my vapor dome. And I know there's going to be some line here that's going to be 100 psi. So go ahead and draw my 100 psi line. Now, I need to know where this saturates. Where does 100 psi saturate? So for those of you at home, I'm not going to put this on the screen. I'm just going to look it up in my tables. I'm going to go to my 100 psi table A3. 100 psi shows me that we saturate at a temperature of 327.86 degrees Fahrenheit, where it shows me on table A3, first page. My temperature is well above that at 400 degrees Fahrenheit. So I know that I intersect here. This is my state 1. Again, I don't know state 2, but I know state 3. State 3 is at 300 degrees Fahrenheit, which is well below this. It's at 300 degrees Fahrenheit. So here's 300 degrees Fahrenheit. And I'm going to go ahead and draw a line here. And I know I'm at a quality of 0.6. So I'm going to say probably right there is going to be state 3. And the same process follows. Because between state 2 and state 3 are constant volume, they're going to be constant in a closed system. They're going to be constant specific volume. That means 0.2 is right here above it. This is 0.2. And so here we go. This is my process from 1 to 2, and this is my process from 2 to 3, and we've drawn that line. Now, a very good point was brought up in the 830 class. State 2 and state 3 are on the same specific volume line. This does not mean that the quality of state 2 and the quality of state 3 are the same quality. The quality is showing how far you're going across that line. And as you can see, the line that state 3 is on is longer than the line at state 2. So they're going to have different qualities. Even though the specific volume is the same, they're going to have different qualities. We're going to be 60% along the line on 3. We're going to be somewhere north of that in state 2. Okay, let's now draw our PV diagram. Our PV diagram, we now draw our vapor dome, and we now have 400 degrees Fahrenheit is the line that we draw. So we're going to go up here, and we're going to draw a 400 degrees Fahrenheit line, 400 degrees Fahrenheit, and we're going to look in our tables and find out where do we saturate at 400 degrees Fahrenheit, and we find that we saturate at 247.1 psi. We're well below that. We're at 100 psi. So we intersect with that line right here. This is our state 1. Our state 2 is at 300 degrees Fahrenheit. Okay, I go to 300 degrees Fahrenheit in my tables, table A2E, and I notice that it saturates at 66.98. So it saturates down here at 66.98. Okay, so here we're going to have a line. This is my 300 degrees Fahrenheit, and my state 3 is going to be still 30% right here. This will be my state 3. Where is state 2? State 2, we go from 1 to 2 on a constant pressure line, and we go from 3 to 2 on a constant specific volume line, so this is going to go like this. This is my state 2, and this is my process, and this is how I go. As we're going from state 1 to state 2, we are changing temperature rapidly. We would have a whole bunch of different lines that we are going through. Okay, as we're going through there. So the diagram looks very different, but tells us the same stuff. Okay, and now we're going to go through here and we are going to start setting states. Okay, state 1, superheated vapor. State 2 and 3, both mixtures. All right, so I'm going to give you those values. Okay, I'm going to give you those values. So state 1. The specific volume of 1 is equal to 4.934 cubic feet per pound. And the internal energy of 1 is equal to 1136.2 BTU per pound. Nice, even lookups, no interpolation, 100 psi, 400 degrees Fahrenheit directly on the chart. Can't do anything for state 2 right now. I do know that state 2, the pressure at state 2 is going to be equal to 100 psi. So the connection between state 2 and state 3 is my specific volume at state 3, so I will set my state 3 first, state 3. And I'm going to use the quality equation. So I'm going to say using quality equation, I am going to find that my specific volume of 3 is equal to 3.89 cubic feet per pound, and that the internal energy at 3 is going to equal to 767.8 BTU per pound. Okay, now, that leaves me with state 2. State 2 is going to say, I'm going to say that V2 is equal to V3, and I have to be at 100 psi. And I'm going to know that at 100 psi, that my Vg, now let's do it this way, Vf, my value of V2 is somewhere between my saturated liquid and saturated vapor. And so I'm going to set an equation that says V2 is equal to Vf plus X times Vg minus Vf. And because I know everything in this equation except for X, I will solve for X and find out what the quality is for X. Quality is for state 2. And that's going to give me that it's 0.877 or 87.7. So it's not the same quality as state 3. It's actually much higher than that at state 3. And then now that I know the quality, I will use that quality to find out what U2 is. And U2 is 1006.48 BTU per pound. And now that I have all these states figured out, now I can go and use the first law and use the work equation to find out what my work and my heat are. And again, I'm going to give these to you as the answers. I would like for you to work through and verify these answers. This would be a good effort for you. So I'm going to just tell you that work 1-2 is equal to negative 38.64 BTUs. Makes sense that it's negative because the surroundings are working on the system. The heat transfer from 1 to 2 is equal to negative 298.08 BTUs. The work from 2 to 3, it's constant volume, that's going to be equal to 0. And the heat transfer from 2 to 3 is going to equal to negative 477.36 BTUs. So while because of time we didn't go through and do all those calculations, I would put a star on this, and when it comes to the next exam, make sure that you can go through this and find those, because depending on time, these are a little bit more involved problems. Depending on time, this would be a good problem to put on the exam to make sure that you can follow a constant pressure, constant volume situation. In fact, you had enough information really in the first exam that you could solve this problem. You did. There's nothing new here. This is an exam 2 problem. I could have given you exam 1, but you have not matured into the idea of thermo that you had this all figured out yet. This is going to become second nature to you as we get going through the study. But it's really nothing new here. It's just trying to think through that process. What questions do you have today? When you redo the test, I would like for you just to print out the test again on that sheet I have there and just redo it on that and then scan it in. If you don't have a printer, and a lot of people don't have a printer, you can do it on white paper. But I think you have access to engineering printing, so just print it out. That's what I would prefer it on. And if you do it on white paper, you do not have to rewrite the problem statement. You do not have to follow homework formatting. You do need to box your answers, because the graders are going to be looking through and making sure that we're looking at answer alone. Yes, we're going to make sure you have to show your work. You can't just show me just write about a bunch of answers. You have to show your work, but we're mainly concerned with that answer. That's how you're going to get the extra credit points. Any other questions? Okay, glad you were here today. Have a good rest of your week, and we will see you on Friday.